Hi, this is Zhao Chen from KAUST, presenting our work Resquare TAL. Long-form video understanding tasks, such as temporal action localization, is extremely memory-intensive to train end-to-end. To facilitate memory-efficient training, we propose Resquare TAL. Given any residual modules, such as restant blocks and self-attention blocks, we replicate the input and rewire the skip connections to convert it into a new module with the same parameters. The network with the new modules can reuse the parameters in the previous module without training from scratch. The obtained module is reversible, meaning that we can reconstruct the input from the output. Therefore, the intermediate features don't need to store in memory for backpropagation, and the GPU memory usage is dramatically reduced. Let me describe this work in more details. Temporal action localization, TAL for short, aims to recognize actions in a long video and localize their start and end time stamps. It is a typical long-form video understanding task, which needs to reason among a large number of video frames. This is a widely adopted TAL architecture, which comprises a backbone and a localizer. The backbone, such as slow fast and video swing transformer, extracts short-term video features. The localizer, such as VSGN and ActionFormer, performs a long-term temporal aggregation and outputs the prediction results. The ideal of training TAL is end-to-end, meaning training the backbone and the localizer at the same time. But it is extremely memory expensive in the backbone. This is because during training, all the intermediate activations from all frames need to be stored in memory for backpropagation. Therefore, most works adopt two-step or feature-based training as a compromise, which first extract short-term features using a pre-trained backbone and then train the localizer only with the pre-extract features. This inevitably sacrifices the accuracy, since the backbone cannot adapt to the TAL task and the dataset. If end-to-end training is the way to go, can we find such type of a network as the backbone that uses less memory but achieves comparable performance? The answer is yes. Reversible networks, which can reconstruct the input from the output, don't need to store intermediate activations in GPU memory, thus can dramatically reduce GPU memory usage. Multiple reversible networks have been proposed in the literature to reduce memory while preserving accuracy, such as RevVIT and RevNet. However, these works only focus on specific architectures, and their models need to train from scratch. Therefore, it is not a good idea to directly apply these reversible networks to TAL, which needs multiple rounds of backbone pre-training on different datasets to reach a good performance. To facilitate end-to-end training with minimal pre-training effort, in this work, we propose Resquare TAL. Let's consider one commonly used structure in modern neural networks, the residual module, which has a skip connection around a stack of operations. For example, the restant block or the self-attention blocks in transformers. Given any residual module, we can convert it into a reversible one by rewiring, such that we can automatically obtain reversible networks from the large collection of various existing or even future network architectures. The rewiring process is as follows. Here is a network of 3 residual modules. We make a 2-pathway network by rewiring. We replicate the original input as the input to the second pathway and rewire all skip connections to make them skip 2 blocks instead of 1 block to convert that network into one network with 3 new modules. The new network had the same parameters in F1, F2, and F3 as the original network. Thus, it can reuse the parameters without training from scratch. The rewired network is reversible or invertible, which can be easily proved with the mathematical formulations. This is the obtained forward process, and this is the reverse process to reconstruct the input from the output. Due to the reversible property of the network, we don't need to store intermediate activations in memory and can reconstruct those during backpropagation. Therefore, GPU memory consumption is dramatically reduced. The steps of using the rewiring strategy for TAO end-to-end training is the following. Prepare a video model with pre-trained parameters. Rewire the residual connection in the model as proposed. Load the pre-trained parameters into the rewired model. Fine-tune for several epochs on the pre-training task. And it is ready for use for TAO and other tasks. Experimental results. We compare original non-reversible networks to our rewired reversible counterparts in terms of memory consumption and accuracy. We experimented on different variants of video swing transformers and slow-fast networks. For all the variants, our reversible networks use significantly less GPU memory, and their use of memory keeps constant as the networks become deeper. At the same time, the accuracy of our rewired reversible networks is comparable to the original non-reversible networks. This table shows the min-AP comparison with the previous representative TAO methods on the two datasets, ActivityNet and TUMAS. Our squared TAO sets a new state-of-the-art performance on ActivityNet and reaches the highest among all RGB-only methods on TUMAS. If we compare the results of ReSquared TAO end-to-end training to their counterparts of feature-based training, ReSquared TAO significantly improves the performance. Conclusions. We proposed a rewiring strategy to convert off-the-shelf models into reversible models without the need to design or train from scratch. Using our ReSquared models, we can do end-to-end training with dramatically reduced memory cost and achieve significantly higher accuracy than the two-step training. We demonstrated the effectiveness of our ReSquared strategy with the memory-intensive task temporal action localization, TAO. The strategy and the models of ReSquared can also be applied to other tasks. You're welcome to try it. Thanks for the attention.